Okay, now we're going to continue on and learn how to use scientific notation. Scientific notation is used to express very large or very small numbers. So here's what scientific notation looks like when you see it. This part is called the decimal part. And later on, we're going to learn that this, you look at the decimal part for significant figures. So I'll say used for sig figs. And if that doesn't make sense right now, that's okay. The other part of scientific notation has an exponential term. Okay. So the negative, what does that mean? Well, this number is actually a really small number, 1.2 times 10 to the negative 10th. So that means that you have 0.000000000, 3, 4, 5, 6, 7, 8, one more 0, 0, 1, 2. So to get this number to scientific notation, the decimal had to be moved 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the right. So that's why we get 10 to the negative 10th. And then our decimal part is this portion. The new decimal is right there, 1.2 times 10 to the negative 10th. So usually when you're asked to express something in scientific notation, you want to have it, I'll say the standard form is something like this, where you have your number, decimal, and then whatever digits after that times 10 to, I'll put negative x up here. So when I say express the number 5,467 in scientific notation, what I'm wanting is this decimal, which is now implied, so it's not explicitly, there's a decimal right there. I want you to express it so it looks like this, 5.467. And so in order to write it like that, we would have to move the decimal 1, 2, 3 to the left. So that means our exponential term would be times 10. And since it's to the left, it's going to be a positive number. Okay? So let's go to the next example. Express the number 0.000348 in scientific notation. Again, we're trying to get to the standard form of scientific notation, so we're going to have to move the decimal over to the right. 1, 2, 3, 4. So it's 3.48 times 10 to the negative 4th. So on the next page, I have practice problems on representing the following numbers in scientific notation. So what I want you to do is hit pause, work through these, and try your best to get the correct answer. It may not be that you get the correct answer the first time, but just try. Part of chemistry is trying and failing, and then succeeding. So you have to keep kind of trying in all these different things. So hit pause, work these problems, and then come back to it and I'll go over the answers. Okay, so this one would be 1 to the left. So this is going to be 1 to the left. So it will be 5.40 times 10 to the first. Now, if you left this 0 off right here, that's okay. We will learn more about significant figures later on, and you'll learn that that is a significant figure and that it needs to be expressed. But don't fret if you didn't have that. I wouldn't count off on it right now. Okay. This one needs to go 3 to the left. So it's 1 to the left. So that's going to be 4.567 times 10 to the third. The next one is just 1 to the right. And your answer would be 3.45. And all these zeros are significant. Not that I expect you to know that yet. But so just for good practice, I'm going to copy those down because they are significant. So it's 3.45000 times 10 to the negative 1. All right, this next one, D. Your decimal is here, and it needs to be moved 1, 2, 3, 4, 5, 6, 7. So 7 to the left. So that's going to be 1 actually, because those aren't significant, times 10 to the 7th. E, you're going to move the decimal 1, 2, 3, 3 to the right. So it's going to be 9.078 times 10 to the negative third. All right, F, 540. There's a decimal right here that's not explicitly written. So it's going to be 1, 2, 2 to the left, 5.4 times 10 to the second. G, the decimal needs to move 3 to the right. So that's going to be 3.040 times 10 to the negative third. And then the last one, the decimal is going to go 1, 2, 3, 4, 5, 6, 7, 8. So that will be 2.00567,987 times 10 to the 8th. So it was 8 to the left. So if you had trouble on any of those, practice, practice, practice. There are some textbook problems, some homework problems from your textbook that you can work, and the answers in the back. So that will give you more practice. Okay, now on the next page, I have numbers written in scientific or standard or scientific notation, and I want them converted to standard notation. So this is doing the opposite of what we just did. So if you're having trouble just first getting a grasp of this, it can be helpful to just kind of get a feel whether this is going to be a large number or a small number. Look at the exponential term. Okay, 10 to the third is going to be a large number. 10 to the fourth is going to be a large number. 10 to the negative fifth, small number. Negative third, small number. 10 to the sixth, large number. 10 to the negative second, small number. So you get an idea, because sometimes students will get going the wrong way. So this will be large large, small, small, large, and then small. So that way, if you get flipped around, you can kind of think back and say, oh, wait a second, this is supposed to be a small number or a large number. Okay, so now you're doing the opposite. So 10 to the third, that means you had to move the decimal 3 to the left to get it in this term. So now you're going to have to get it out of this term, you're going to have to go 3 to the right. So it's the exact opposite of what we did. So 1, 2, 3. So 12, 3, 0, 0. All right, so this one you're going to have to go 4 to the right. That's where the decimal is going to go. So it's 1, 2, 3, 4. Okay. Now this one is a negative term, so in order to get that negative term, you move the decimal to the right, but now you're going to move it to the left. So to get it, so it's going to be 5 to the left. So that's 1, 2, 3, 4, 5. So 1, 2, 3, 4 zeros after the decimal. And then, okay, you had to move it to the right to get negative third, so you're going to do 3 to the left to get it out. So 1, 2, 3. Now, if you didn't have those zeros after the 3, that's okay. It takes a little practice in knowing significant figures. Alrighty, so this one, you moved the decimal to the left to get this exponential term, so you're going to move it 6 to the right to get it out of scientific notation. So 1, 2, 3, 4, 5, 6. So that's 1, 2, 4 zeros. 5, 6, 1, 2, 3, 4 zeros. And then this one, you moved it to the right to get that negative, so you're going to get it out of it, you're going to move the opposite. Kind of like if you take a right turn to get somewhere, to go backwards, you're going to end up taking a left turn. So 2 to the left. So end up with 1, 2. Okay. So there you have it. So again, if you're having trouble with scientific notation, be sure to practice, practice, practice. Come to my office hours, ask questions in class, or go to the SRC. So, moving on, now we're going to learn about significant figures. A lot of students who have taken a chemistry course and did not succeed in completing the course, one of the main things they struggled with was significant figures, sadly. Significant figures are something that is an important concept all throughout your chemistry course. They don't go away. Even though students wish they would go away, they do not go away. So it's very important to have a firm foundation in what scientific figures or significant figures, what they mean, why you use them, why you pay attention to them. Do they matter? Yes, always, even though you'd like to forget them. So significant figures. Usually this makes students cringe, but I hope after my explanation that you will learn to respect significant figures. Okay, there are two types of numbers that we deal with in science. They're measured numbers and there are exact numbers. Now, measured numbers are obtained from measuring something. So they're obtained from measuring something. Volume with a graduated cylinder, temperature with a thermometer, mass with a balance, height with a meter stick, whatever it may be, they are obtained from measuring something. So significant figures matter. So very important. Now, exact numbers. These are obtained by counting. Okay, so I have 24 students. I have 12 eggs. With exact numbers, significant figures do not matter because you're just counting. So you wouldn't say you can only use 3 sig figs, so you have 24.5 students. You would never do something like that because you're just counting bodies. So significant figures matter when you measure something. And in chemistry and in a lot of the sciences, there are many measured numbers. So if you weigh a tennis ball on a bathroom scale, you get 0 kilograms. And you think to yourself, I know it has mass. I can feel it. It does not weigh 0 kilograms. If you weigh it on a laboratory scale, you get 54.07 grams. If you weigh it on an analytical balance, you get 54.07138 grams. So, what does this mean? So, what this tells us is precision of measurement is indicated by the recorded value using all the digits known with certainty, plus one additional estimated digit. So what that means is that the bathroom scale only is accurate or is precise to the ones place. So when you take your weight on a bathroom scale, 61 kilograms would be appropriate, or 115 pounds, 140 pounds, whatever it is, it's just estimated to that one's place. Now on a laboratory scale, 54.07, this number right here is estimated. So it can be accurate to plus or minus 1. So it could be 54.08, it could be 54.06, and it would still be within error. So an analytical balance is accurate all the way to this 8. So that could be a 7 or 9. So you use more digits for this analytical balance. And really what that means is it's a lot more precise of an instrument because it can measure to the tenths. Very far out. So this digit costs a lot of money to get it. So if you want to look at the cost, this is as you go down, you increase the cost of these instruments. So what I'm getting at here, the total number of digits used to express a measurement is called the number of significant figures. So I have not taught you the rules about how many significant figures, what the rules, any of the rules. But just to give you an idea, this measurement, and remember significant figures matter with measured numbers. This measurement, 1, 2, 3, 4, 5, has 5 significant figures. This one only has 3. It turns out that these zeros are just placeholders, and we'll learn that coming up. All right, this one only has 4, but this 0 in the middle counts. Okay, this one, these are just placeholders, so it has 4. These are just placeholders, so it has 2. So let's learn the rules, because being able to determine how many significant figures are in each of these measured numbers is a huge skill that will take you very far in chemistry. And if you don't learn anything else from this course, if you learn your significant figure rules, that can be extremely helpful. Okay, so rule number 1. Zeros in the middle of a number are significant. Okay, so it's 94.072 grams. This has 1, 2, 3, 4, 5 sig figs. Okay, rule number 2. Zeros at the beginning of a number are not significant. They are placeholders. All right. So when you look at the number, measure number 0.0834 centimeters, these do not count. They're just placeholders. So this has 3 sig figs. All right, rule number 3. Zeros at the end of a number before an implied decimal point are not significant. They're placeholders. So 138,200 meters. These zeros come before an implied decimal point, which would be here. So this is implied. So these are not significant. Now, if I had something like 138,200 and the decimal point is explicitly written, then I would have 6 sig figs, whereas here I only have 4 sig figs. So this is explicit. Okay? Rule number 4, zeros after an explicit decimal point are significant. Okay, so this measurement has a 0 after the explicit decimal point. All of these zeros matter. So this is 3 sig figs. Okay, so I want you to practice. How many significant figures are in each? Well, this one has a 0 in the middle. That's rule number 1. Everything else counts, so this is 5 sig figs. This one, the zeros in front, are they significant? No, they're placeholders. So this is 3. Okay, same thing here. We have zeros in the front, they're just placeholders. So 1, 2, 3, 4. So that's 4 sig figs. This one, these come before an implied decimal point, so they do not count. So it's just 4. And this last one, 23,000 miles, they come before an implied decimal point, so it's 2. All right, how many significant figures does each of the following measurements have? I want you to hit pause and work on these. And then come back and hopefully you've gotten some correct answers. Because really, significant figures can be very challenging for students. So getting these straight now and will be very helpful. And we'll learn operations, multiplication, division, addition and subtraction with significant figures, and that makes a big difference too. So go ahead and work these. Okay, so this has 6 significant figures. This has 2 significant figures. These are placeholders. B and C are placeholders. And this has 2 significant figures. Now, look at D. D has an explicit decimal point. So those are not placeholders anymore. Those zeros count. So this is 1, 2, 3, 4, 5 decimal point, or 5 significant figures. Okay, so I will stop here. Practice, practice, practice your homework problems.